Hello and welcome to another LeetCode problem. So today we're going to be doing problem number 129, sum root to leaf numbers. And so we're given a root of a binary tree containing digits from 0 to 9. Each root to leaf path in the tree represents a number. And so for example, the root to leaf path 1, 2, 3 represents the number 1, 2, 3. And so what we need to do is we need to return the sum of all the root to leaf numbers. And so let's do that. So actually they're by the way, I misspoke a little bit. So they're saying if you have a 1, 2, 3, what you actually need to do is like, you need to, these are all different values of tens, right? So the leaf is going to be the 0th index, and then it's going to be the first index and the 1th index, right? So it's like 3 times 10 to the 0, 2 times 10 to the 1, and then 1 times 10 to the squared, and so on. Okay, and so let's draw this tree. Think about how we would actually do this. So we want to return the sum of all root to leaf paths. How would we actually do that? That is the question. So let's take a look at this one. So this is kind of straightforward, right? Like once we get to a leaf, we can just return the value of the leaf. So we can just return 2 up here, and we can return 3 up here. And then we can just say like, okay, well, whatever value we have, let's just, we probably need to know like what level we are at. And then we need to return the level like times 10. So this would be like level 0, level 1. So we need to figure out how many levels we went up. Alternatively, what else can we do? The other thing we can do is whenever we have some number, if we don't know the level, so what we can do is, let's say we do return 2 and 3. Well, what do we really need to do? So we have a number 2, and what we really need to do is just figuring out like what this number is, and we just need to add a whatever this number is in front of it, right? So let's say it's a 1, so we just need to add a 1 here, and then we have a number here, and we just need to add a 1 here as well, right? So it'd be like 1, 3. So that's another thing we can do, and then we can add these together, and then we get a sum. Let's actually look at example 2 and try to figure out like how we would do this, or if there's something better. So let's take a look. So we have 4, 0, 9. Yeah, if we don't want to do the levels, then what do we have to do? Or we could actually do it a different way, even. Now that I think about it. So what we could do is, instead of returning these, we can just pass down, because that would be kind of easier, right? Because like the problem with this is like what paths do we have? So we have this path right here, right? This is 495. Then we have this path right here, 491. We have this path, which is 40. So instead of doing what I said earlier, where we like return the numbers, we can actually do something a little bit better. So what we can do is we can just have an input variable into like the root. So let's say we just have a root, and then we have some input variable, and then at every node we take whatever input integer that is, multiply it by 10, and then add the current number. So what's that going to look like? Okay, well, let's take a look. So we're going to go into the root, we're going to pass in a 0. Then at every single index, we are going to multiply whatever number we have by 10 and add the number that's in this. So let's try that. So we're going to multiply 0 by 10. It's going to be 0. We're going to add 4. And then we're going to pass that into the next nodes, right? So we're going to go over here. Now we're going to pass in a 4. And we are going to pass in a 4 as well. Now at every node, we check, is it a leaf node? If it is a leaf node, that means we have a root to leaf path. And we're actually given the value, right? So we have this 4. And so we can see, okay, we are at a root to leaf path. So what we need to remember, we need to multiply whatever number we have by 10 and then add whatever's in this. So this would be 4 times 10 plus 0. So that's 40. And then because we are at a leaf, we're going to append it to some result. So that's going to be 40. Now we go down here. So we put in a 4. And now what do we do here? Well, like I said, we have to take whatever number we have, multiply by 10, and add the 9. What we could also technically do, by the way, is instead of multiplying by 10 like multiple times, what we could actually do is we could, let me redo this. So what we could do is when we pass down, we can actually multiply the number we pass down by 10, right? So we have a 4 here. So instead of doing this by 10 here, what we could do is we take this 4, we multiply by 10, then we pass it down. But first we check, like, are we at a leaf? But if we're not at a leaf, then we take this 4, we multiply by 10, pass it down. So we'd pass down 40 here, and we'd pass down 40 here. So let me actually redo that. Let's delete all this. And let's actually delete this stuff here to make it. And I'm actually going to show you what that's going to look like. Yeah, okay. So we're going to redo this one more time, and this is what we're going to be doing. So we have a 0, then we're going to check, are we at a leaf? We're not at a leaf. That means we need to pass down this value to the children because we're not at a leaf. But instead of passing down the value, we're going to pass down the value multiplied by 10. So we're going to pass down 40 here. We're going to pass down 40 here. Now we check, are we at a leaf? Yes, we are. Okay, that means take whatever's passed in, add the value at our current node, and append that up here. And so that's going to be 40. Now we're over here. Are we at a leaf? No. So take whatever value is here, add that to a 9, so 49. Then we're going to pass that down to the children. So this is 49, 49. Now we check, are we at a leaf? Yes. Okay, so take whatever value was passed in, multiply by 10. Actually, so sorry. Remember, when we pass down, yeah, so I forgot one thing. So when we pass down, remember, we're not passing down 49. We're actually doing the multiply by 10 if it has children. So we're actually going to pass down 490 into both of these, right? So we're going to pass 40 down into here. We're going to add the 9. We're going to check, do we have children? And if we do have children, then we can just take our value multiplied by 10 now and then pass it down. So this is going to be 490. This is going to be 490. Now we check, are we at a leaf? Yes. That means we don't need to do any multiply by 10s, but we still need to add the value. So we need to add the value regardless of if we're at a leaf or not, right? So whatever value is passed in plus the value of our number. So and this is going to be 491. And because these are both at a leaf, this is going to go up here. That's going to go up there. And we can just say if we're at a leaf, then just update our output. And so our, pseudocode, let's just say, is going to be pass in some value into a node, into like a helper function. So value plus node, so value node into helper function. Just do that over here. Okay, we're going to add per value plus the value. And then we have two cases, right? So if children, then I'm kind of running a space here, but that's okay. So if children, we are going to, so we take this current value plus value. So then we do that value times 10 into children. And if there's no children, then we just append to res. So whatever the current value we have, we just append to the result. So that's our algorithm. We're gonna put in a value and a node into a function. We are going to add the node's value to that value, and then if there are no children, we just straight away put that function into the result. And if there are children, then we need to multiply our current value by 10 and then put that into the next node. And so we're actually going to be updating the results in every leaf node, because the problem with like recursing back up to the root is it's kind of hard, because like if you have a bunch of paths, like how do we actually get all these values? Like even here, like if this is 95 and 91, I mean, we could technically return 95 and 91, but the problem is once this tree gets big, you're going to be returning like huge arrays of values. So it's better to just pass things down into the leaf nodes and then handle the, getting the actual values there. So let's do it that way, and let's code that up. Okay, so we're going to define a helper function here. So let's just say this is called root to leaf maybe. And it's going to take a node and a value. And so regardless of if it's a leaf node or it has children, we need to take whatever values passed in and add the value of the node. So let's do that. By the way, do we need to check for a root being number of nodes? Okay, so there's guaranteed to be a root, and then we're just going to double check here that we're not going into any null nodes. So if there are no like left and rights, we're not going to traverse down. Okay, so we're going to say, we also do need a result here. And I think the result is just a number like this, where we just need to we just need to keep adding to the result every time we get a value once we're in this like leaf. So when we're at a node, we're going to do, let's just say cur maybe equals node.val plus val. So like in this example for this 4 in this root, we're going to pass in a 0, so this will be a 4. Now we need to check for children. So if there are no children, we need to update the result. And if there are children, we need to pass that value into the, we need to take the value, multiply by 10, and then pass it into the children. And so let's do that. So if not node.left and not node.right, meaning there are no children, now we just need to do this, and then res plus equals cur. And if there are children, then we need to update our value. So we need to multiply by 10, right? So if we have a 4 here, we need to multiply this by 10 and pass it into our children. So we pass the 40 into over here and over here. So we're going to handle that in the node. Okay, so we're going to multiply by 10. Now we need to pass it into the left and the right, and we need to check for the left and the right. So we're going to do that. So if node.left, then we're going to do a root. And so we don't want to go into null nodes here. And then this is going to be cur. Same for node.right. Cur. Okay. And so let's actually do one more time. Let's actually show what this algorithm would look like cleanly for this tree right here. Okay, so let's go over it real quick. 0, 5, 1. And we're going to show like what node we're at and what we do. And we're going to have a result. So let's just make the result 0 at first. And then we're going to keep adding to it. So we're entering this node with a value of 0. Then we add that value of 0 to the value of the node. So we're going to get a 4. Now we say, does it have children? Yes, it does. So instead of a 4, we need to multiply by 10. So we get 40. So we pass 40 into here. We pass 40 into here. Okay. So we have 40 here. We add the value of the node. So that's just 40 plus 0. So that's 0. We say, are there any children? No, there's not. That means we take this value, we put it into the result, so 40. Okay, now we go down here. So now we have 40 plus 9, 49. Now we say, are there children? Yes, there are. So we need to multiply our number by 10. So we get 490. Pass it into both children. So we have 490. We add the 5 here, and we add the 1 here. And we ask, are there children? And there are no children in either of these. So then you're going to add both of these to the result. So you get 495 plus 491 plus 40, which is what they wanted, I believe. Let's take a look. Yeah. Okay, so it looks good. So that's pretty much what our code does. Let's see if we screwed up as always. Of course. Let's take a look. So, oh, right. We never actually called our function. So we need to call root to leaf on the root, and we need to give it a value of 0 to start off. There we go. All right. And so let's think about the time and space here. So when we are traversing, we are going to traverse down into every single node. So that's going to be a big O of n, and we're only traversing once. We're just doing like a, what kind of traversal would this actually be? So we're going root left, right, technically, I think. Yeah, I mean, yeah, it's kind of like, I guess we are checking the root value first, so it's going to be like a pre-order traversal technically, I guess. But whatever, it doesn't really matter too much. Either way, we're going into every single node. So that's going to be big O of n, and where n's a number of nodes. Space. So are we making anything extra? No, we're not, but our worst case scenario here is, as always, so this is a binary tree, but it's not guaranteed to be a binary tree that's, I forgot the name, not sorted, but like not complete either. I think it's balanced. Yeah, balanced, meaning you can have something like this, right? So we can have things like this, like 4, 5, Like we can just have all the nodes on one path. And so then you would have to recurse down. Like if this was n nodes, you know, if this was 6 nodes, you would have to recurse all the way down. And so the recursive call stack would keep growing. So this is O(n) as well for a tree traversal, unless this was balanced. If this was balanced, it would be like log n, I think. But it's not guaranteed to be a balanced tree. So worst case scenario, we just have to go down every single node in one recursive call. That's going to be O(n), and I think that's it for this problem. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. It helps grow it a lot. Thanks for watching, and I'll see you in the next video. Bye.